Let's move on to Dinesh Rao's talk, uh, an insect's view of orb webs in different light environments. All right, Dinesh, why don't you unmute yourself and take it away?
Thanks, Bob. So my name is Dinesh, and I'm from the Universidad Veracruzana in Mexico, and today I'm going to talk about an insect's view of orb webs in different light environments. So the first thing to emphasize is that each species looks at the world in a completely different way. It's an echo of von Uxel's concept of Umwelt, where an animal's perceptual world is primarily dictated by the characteristics of its sensory physiology. So, for example, in this flower with a spider on it, this is how it looks to us. But if you take into account the color sensitivity of a potential prey like a honeybee, which can see in UV, blue, and green, you get a completely different picture. And this is a simulated image with coded for honeybee vision. But in addition to this, you also need to take into account visual acuity, which is that at different distances, the objects look slightly more fuzzy or more blurry to these insects. So this is a simulated image of what it would possibly look like at, say, 10 centimeters away from the flower. And if you bring in these concepts into orb web visibility, there are many factors that could influence how visible a web is. It's first is the light environment, whether the webs are in open areas or if they're in the undergrowth, the visual system, as I mentioned earlier, and from the spider side, the color of the spider, the plane of the orb web, so horizontal webs or vertical webs, or even webs that have both planes in them, and the web strand density, so the mesh, different spiders make webs of different mesh sizes, density, and even within the same spider, you could have, same web, you could have different mesh densities, for example, here and over here, and the presence of web decorations, which are these extracellular structures attached to the web. All these affect our web visibility. In this talk, I'm going to focus on light environments. So when I say light environments, I'm just usually referring to how the angle of light, the sun rays falling on the web. So if you have a web like this and the sun rays are falling at an angle, you get a iridescent coloration. Or if the sun is behind the spider web, you get a backlit condition. This is usually in the evenings or in the mornings when we can actually see webs more clearly. And over here you have a front lit when the light is, this is from a flash, but the concept is the same, that the flash is falling on the web from the front and you can see the web more clearly. So insects should be capable of seeing these colorations and detect the webs easily, or well, better. So the only study about this has been done in the 80s by Kathleen Craig, who looked at insect flight patterns as they approach different webs. And integrating insect movement into this is important because insects are never still and they're moving around, and they're getting different views of the web or the predator. And here is a flight path of a Drosophila fly as it's flying towards the web here, which is one of these Theridiosomatidae webs. And these are acceleration vectors at different points. And you can tell that there is a small gap just before it hits the web, where it realizes the presence of web. So they are capable of detecting webs in mid-flight. But these experiments were done in really controlled conditions with well-lit laboratory setup. And there was a nice background, contrasting background for the web. And it's always hard to tell whether an insect is just trying to escape from the box or would it do the same flight in natural conditions. So to explore this, I used this Allocyclosa bifurca as my study species. Here's the spider. This is an egg sac and kind of looks roughly the same coloration as the spider. They build these nice vertical orb webs and quite small. This is a 20 by 20 centimeter frame that they're building in. And we looked at the hoverfly of this species, Spherophoria species, as a potential prey. And I had 4 treatments. We had the web under shade, which is just blacked out the sun with a cloth, and so that there's no sunlight hitting the web. And then you had the sun overhead, so the angles are just of the rays of sun are just from the top. The sun in the front to simulate a front-lit situation, and the sun in the back to simulate a backlit situation. So this was my rough idea of a visibility gradient. So this would be more visible than this. And the experiments were quite simple. Here is the frame with the spider web in it, but it's filmed from the top, so you can't see the web. And this is again 20 centimeters. And the hoverfly is going to come from this direction. Is going to come from the bottom part of the screen and approach the web. So the flies are really small, less than 1 centimeter, and it's quite hard to make out in this video. And so we tracked all the flies that approach the web. So you can tell it comes very close to the web and then heads out over there. And all this tracking was done in ImageJ, a plugin called mTrackJ, or manually tracked to get these trajectories. So the first results were not significant. So basically, there was no difference in terms of whether the flies were more likely to avoid the web or hit the web according to the treatments. But there seemed to be a tendency here that they're more likely to avoid when the sun was either overhead or shade, which is counterintuitive or goes against our prediction that that these are the less visible parts of the web. And the only case where there was more impact, relatively more impact, was when the sun was in front, it's a frontlit situation. But the numbers aren't very high, so we looked at this data in a different way. The first thing was to incorporate visual modeling, and this we did by using a full spectrum camera and taking 2 photographs, one in visible light. This is how we would see the web, and this is in UV. And then we used the information available from the receptors of a model hoverfly and incorporate that into creating a simulated image of what it might possibly look like to a hoverfly. Not that they have 2 receptors in the UV, so which is coded to yellow in this image. And you can still tell that you can still make out edges of the parts of the web in this image. However, if you take into account visual acuity at different distances, you can see differences. All these 3 images probably look the same to you on the Zoom presentation, but there are differences. At 20 centimeters away, the details are very blurry. You can still see the X-axis. The spider is not present in these photographs. It's just the X-axis. And you can just about barely tell that there's a web there. But within 5 or 2 centimeters, you can make out more details of the web structure, especially when the background is a little more darker. Note that there's a lot of UV reflectance from the leaves on the background, which causes a lot of noise. And so we looked at some sample trajectories where it shows the different strategies used by these hoverflies. In this case, the fly starts over here, and as it approaches the web, this red dotted line is the web. It's all to scale. You can tell that because of the sharp turn it makes here, it's probably detecting the web at this distance and slowly evaluating the whole structure before moving away. In this case, the fly actually hits the web. There is an impact, but there's not enough to be captured. It bounces back at kind of at a safe distance, so to say, and then slowly evaluating the web, and then it moves around the frame. Whereas in this case, the fly is flying rather fast. You can tell by the distance between the points, and actually goes through the web without really impacting it. So probably through a gap in the frame, or and then changes its trajectory after it passes through the dangerous part. So we did analysis looking at the speed. So one of the ways that they can successfully detect the web is by changing the speed. And this is the same trajectory as we saw earlier, and it's now color-coded according to speed, with the highest speed being a lighter color and the slowest is a darker blue. And the first thing you can tell is that as they're further away from the frame, which is this red line, they're faster, and the slowest part of the trajectory is actually when they're doing the evaluation. So they're probably using speed as a way to make sure that they're paying attention to the threat.
10 minutes.
And thanks. And then if you plot all the trajectories together, I have to note that this is preliminary data, so I don't have stats for these. But it seems to me that as they get closer to the web, which is at 0, 0, the speed decreases, or the speed stays roughly between 30 centimeters per second to 50. And there seem to be differences in different treatments between at least the points below, which is the shade treatment, and the sun overhead. There could be differences, but it's still early days for this. Another way that we can evaluate how hoverflies are responding to the webs is by looking at the structure of the trajectory. And for this, we used curvature as an indicator. So basically, this technique is by putting in a circle at a tangent at each point. And if the trajectory has a straight section, the circle would be much bigger compared to sharp turns would give you smaller circles. And the inverse of this value of this radius is called curvature. And we plotted this against the distance to the web. So this is a complicated figure. So I'll go with one axis first. And this axis is your curvature values. Smaller circles, sharper turns on the top, and larger circles, straighter paths at the bottom. So if you look at this distribution of values, the hoverflies tend to have, the majority of the time they do straight paths, and very frequently or very infrequently they do sharp turns, right? So that's to begin with. And then over here with distance, you can see that there's a density, in this density plot, you can find that there's a peak of kind of in this heat map, you can say more density around between the 5 to 10 centimeter range. There are more points, suggesting that when they're closer to the web and they're evaluating the web, they tend to fly in straight lines and not make the sharp turns. So there's a distinction between evaluating and escaping. So in summary, hoverflies can detect spider webs at a very close distance, and light environments have a partial effect maybe on web detection. And these flight trajectories are a window into the decision-making processes that the hoverflies do in natural conditions. And my take-home message would be that different pollinators respond to predation threat in different ways according to the perceptual capabilities, and underlies the importance of species-centric studies. Thank you, and if you have any questions.
All right, thank you, Dinesh. We have time for questions. Sean McCann asks, could the same be done for Odonata?
Yeah, it could be done. I mean, it could be done for any. It works best if the spider, the predator, is immobile and stays in one spot, so you have a place to film it, and you can watch approaching predators easily. The camera setup was not great. It was just like a regular film camera. The hard part is the tracking, because you have to do it manually. It just takes a pretty long time.
I have a question about was there any wind or air movement during any of the situations, or is it just as still as possible?
Well, there could be gusts of winds, but the area which we did it was kind of sheltered, so it was very low to the ground, so it wouldn't have that much of an effect, I think.
All right, Sebastian Echeverri asks, how strong do you think the acuity or light interaction is as a selective pressure on web design or location?
Well, that's a That's a hard question, because if the spider was a very super specialist, then I would say like it could only eat a certain kind of prey. Then I would say that there could be an effect. But since most of these orb spiders are generalist species, so even if they miss out on the hoverflies, in this case we found very few cases of prey capture. But even if they miss out on the hoverflies, they can still get other insects which fly differently, or they don't have this capacity to hover or slow down, or even grasshoppers or something which can't change their trajectories mid-flight. So I would think that selection pressure would be not so great for visual acuity in particular.
And let's end with this question from Jonas Wolf that I think you alluded to, which is, do you know what the typical prey captured by allocyclosa is?
This is part of a larger experiment where we looked at all prey that we caught, and the majority of them were flies.
Okay, all right, thank you. And you can direct any more questions to him in the chat, and let's move on to George Utz's talk.
Thank you.